Okay, why don't we get started? It's my pleasure to introduce Yoav Sagi, who's coming to us from the Technion. Yoav got his PhD at the Weizmann Institute, working with Nir Davidson, and then went to Jilla and had a long postdoc there, working with Debbie Jen in potassium-40, and then joined the Technion as a faculty member, where he's built up a research group studying both many-body physics and potassium-40, and more recently, atoms and tweezers, which is what he's going to tell us about today. So please join me in welcoming Yoav.
Thank you, Joseph, and thank you all for coming. Please feel free to ask me questions during the talk, okay? So it's really, there's not a syllabus, and I want you to understand as much as you can. So this depiction you see here is some artist concept of an atomic interferometer. So towards the end of the talk, I'll try to convince you that with these optical tweezers that I'll explain, one can maybe hope to do really new kind of atomic interferometry, by which I really mean splitting an atom and recombining. So we'll get there. But because it might be a mixed audience, I'm not sure. Let me put one slide on like the outset. We are talking about ultra-cold atoms. So what do you mean by ultra-cold? Well, this is like a logarithmic scale of temperatures. Oh, sorry, I disturb you. You say, okay. This is us. This is the sun. Here, helium becomes liquid. This is where we are talking about. All the realm of ultra-cold atoms, it's in the sub-microkelvin regime. And why do you need to get here? You need to get rid of all the thermal energy to be totally dominated by quantum effects. And this is where the magic happens. How do you get there? Well, you need to use a bunch of techniques using laser cooling. For example, here you can see the workhorse of the community, what's called the magneto-optical trap, which is a combination of a magnetic trapping and Doppler cooling, which creates these clouds of cold atoms. We also use evaporative cooling, which is very similar to how your hot tea is getting colder, just letting the hottest atoms leave. And then probably the most unique part of these systems is really the fact that they are totally isolated from the environment because they are in ultra-high vacuum systems. They can live for many, many, many seconds without knowing that there is an outer environment. And you can tune many of their properties, for example, the interaction through Feshbach resonance. I'll say something about it in a second. But you can also tune the potential. Here is an example of how you put them in a periodic potential, but I hope all of you know it already from Joseph, because Joseph is an expert on that. And what you see here is actually the depiction of an optical lattice, optical tweezer, which is using a lens to create very tightly focused potential where you actually can trap one or a bit more or a few more of an atoms. Before I get into more details on the tweezer, I do want to show you some bird's eye view of what we do in my group. We have two machines. One is a degenerate Fermi gas machine. It's essentially a machine where we start with, let's say, room temperature gas of potassium-40. Potassium-40 is not particularly interesting by itself, but it's a very convenient atom to work with, and it's a fermion, which allows us to study collective phenomena with fermions. In this system, we cool down a gas of potassium-40 atoms into something which is pretty close to the ground state, not quite, but pretty close, where we see all of these fermions start to somehow behave collectively. So we've been studying a couple of things with this, including impurity physics. What happens if you have, for example, a majority of fermions on one spin, and then you put some minority, some impurity? What happens when you put a balanced gas and they become a superfluid in the what's called BC-BCS crossover? We studied how these gas behave under external modulation, external force, and some other topics as well. This system is a bit different. This is kind of the complementary approach where we, one can say, go from the bottom up. So we put atom in a tweezer, and we can kind of in a Lego build interesting stuff out of that. And with that, we studied spatial adiabatic pulsar, which I'm going to explain, and the interferometry. So that's the main topic of today. But before I go here, I actually want to say one more thing about the gas, because I'm now visiting Joseph and we have a collaboration. I do want to mention this collaboration, which I think is very interesting. So people have studied for a long time the idea of superfluidity with Fermi gases in the so-called BEC-BCS crossover. The idea is that you can tune the interaction using the Feshbach resonance. Here you can see some depiction of that. You see two potentials here. One is of the incoming channel. These are just the fermions that collide. And the other one is of some bound state. This is the red one. And when a bound state becomes resonant with the incoming channel energy, then the scattering properties diverge, and they allow us to tune the scattering properties through the magnetic fields, because these two potentials has a different magnetic moment. And people have studied in this region of strong interaction, particularly my late postdoc advisor, Debbie Jean, and Cindy Regal, what happens when you change the nature of interaction in these around the resonance. And the interesting point is that the pairs that then condense and become a superfluid change their nature from being fermions-like, BCS-like pairs to BC-like, namely tightly bound molecules that condense into embossed gas. And in the strongly interacting regime, there's an interesting question of, are these really bosons, fermions, and how the excitation spectra looks like? People have studied these both by looking on the gas and seeing vortices and studying superfluidity. And the work I wanted to mention that me and Joseph are starting to do now is really looking towards something which is really unique in this aspect, and it's chirality. The interaction that I just mentioned is symmetric. It's S-wave symmetric. It doesn't prefer any direction. But now what could happen if the interaction would prefer some direction and break symmetry? This is the idea of chirality. And what we've came across is a new resonance, a new Feshbach resonance that actually couples two colliding fermions at the same spin. Because these are the same spin, they cannot interact through S-wave because of symmetry. This is precluded. But they can interact through a P-wave, which is the P-wave resonance. And so we discovered this P-wave resonance, which is chiral. So the story goes that we found some unexplained loss that we didn't know. By the way, it's still unexplained. But then by trying to understand this loss in a gas of purely spin polarized potassium-40, we talked to Paul Julian, which is a theorist, and he told us, listen, there is a resonance, but it's not in the right position. This loss was in 143 Gauss, not very interesting. And he said, well, there should be a resonance in 132. And then we went and looked for it, and we found it. And turns out this resonance, it's actually unique in the sense that it's chiral. It couples two states which has different orbital projections. So the bound state and the incoming states have different orbital momentum, which means that it breaks symmetry. So what we are trying to do is trying to think whether this can be actually employed to create chiral superfluids, for example. So that's a very promising direction, and it's all through the collaboration of the Technion and the University of Toronto, which also covers this travel. Okay, so that's about that. And now back to the tweezers, which is the main dish for today. So optical tweezers were invented by Arthur Ashkin, and he actually did it not for the purpose of atomic physics. It was done for biology, to trap biological cells and study, and it's still used for that. But we use it to trap atoms. And the main idea is that atoms are polarized by the light, and then the dipole interaction with the light creates a force. And this force pushes the atom into the points of maximum intensity, which in the case of of these tightly focused beam is just a focal point. I do want to mention that every beam, every interaction with light has two contributions. One, which is the one I just described, it's a two-photon interaction, and it's called the gradient force, and it's proportional to the intensity. You can see it here. But of course, there is also a scattering force that involves spontaneously scattered photons. When we want to just trap the atoms, this is the enemy. And so if we want to reduce it, we need to work at high detuning because it's reduced by another factor of one of the detuning. However, this is very useful as well. This is what allows us, for example, to do laser cooling. If it wouldn't be, we couldn't do that. So both of them are useful. We just have to choose which of them we use. The idea of put neutral atoms into tweezers is gained a lot of popularity in the last couple of years. And this is just one slide showing you what people have been done. So on the left side, you can see people have been pushing the use of this system to use to do quantum computation. This is, for example, from the group of Misha Lukin and Vladan Vuletic and Marcus Greiner from Harvard, MIT. And the idea is really to use the atoms as qubits. You encode quantum information in internal state, and you apply gate between two qubits by just applying interaction using Rydberg excitation. And this has been very successful in reaching really state-of-the-art fidelities. I think the state-of-the-art now is around 99.7-ish, the fidelity of the two-qubit gate. So it's on par with all the other technologies. In fact, this one has a very big advantage of scalability because by just opening many tweezers, one can generate many, one can prepare many qubits. And I think that the record now is coming from the Caltech group of Manuel Enders, where they captured and prepared more than 6,000 of these. So just to make you compare the comparison, maybe you heard about the recent very important result coming from Google, the Google Willow chip, superconducting technology. This result was with 107 qubits. So 6,000 is a lot. Okay, so that's very promising technology, and several groups are pursuing this. People also doing quantum simulation. The difference is here you don't do like discrete gates. Here is really preparing a Hamiltonian and letting the system evolve. Why would you want to use then tweezers? Well, they are very nicely can use to study, for example, magnetic-like interactions. This is coming from the French group of Antoine Boyer, and he has been using this for studying antiferromagnetism and magnetic ordering. This is coming from the group of Wasim Bakr, and you see this has been also been used for Fermi-Hubbard models. So if you just let the fermions hop around, you can study Fermi-Hubbard models. So I already mentioned that here you let the atoms hop around. It means that you actually have tunneling that takes place. I should say that here tunneling is completely forbidden. You want each qubit to be stuck in its own tweezer. But here actually tunneling is an important ingredient of the model. And let me show you that tunneling can also be important to do computation. That's a different kind of computation, but I do want to show you this is an idea of how would you use tunneling to actually generate a universal gate. So universal gates are important if you want to do quantum computation. One of the universal gates is the square root swap, which, as the name suggests, if you apply twice, you get swap. Okay, that's a universal gate. How would you use tunneling and fermionic statistics to implement this gate? So it's actually fairly simple, but you do need to recognize that this gate, the simplest way to actually write it is in the singlet and triplet basis of two qubits. So I just remind you, this is the singlet and triplet states. And the way you would write this gate in a simple form is when the gate applies on a triplet, it does nothing. When it applies to the singlet, you get a phase of I. So it means it's diagonal in this basis, so it's convenient. How would you implement it then? Well, you start with two tweezers and two qubits, okay, two atoms, two fermions. And now initially, think about it as a three-stage process. Initially, you allow it to tunnel. Now, atoms cannot tunnel if they are at the same spin, because this is forbidden by the Pauli blocking, right? So if they are like this or like this, they cannot tunnel. In fact, it's all the triplet states which are forbidden to tunnel because of symmetry. But a singlet can definitely tunnel. It's not forbidden. And so the singlet states actually can after the right amount of time, they can create doublons, double occupation states. Then all you need to do is you need to wait some time. Because these states now have some interaction, they are on the same side, they get some phase because of this interaction, and then again, you let them tunnel back. So the end result is that the singlet state acquired the phase while the triplet did not. And here you go, if you just align correctly this phase, you get this universal gate by just using tunneling and fermionic statistics. So this is an example, and I hope I convince you that tunneling is a key tool really for this type of computation. So what I want to concentrate in the rest of my talk is really on tunneling between tweezers of fermions. This is something we studied, and what can you do with that? So that's the outline of the rest of my talk. I'll show you how we prepare the fermions, how do we see tunneling between the tweezers. Then I'll show you how you can actually use coherent control of tunneling to do transfer between tweezers. This is what's called spatial adiabatic passage. And then I'll show you how it is also used for interferometry. So let's start by one slide on how do we prepare these fermions in the tweezers. So that's again the system we use. And probably the most important part of it is this high numerical aperture objective. This is a cut through the system, and you can see this objective looking on the central plane where the experiment actually takes place. It can create the tweezers with a waist of about 870 nanometers. And the way we prepare the system starts by doing some optical cooling and evaporative cooling. And again, this is not very important. We prepare essentially a cloud of cold potassium-40 gas. Okay, that's the first step. And then when we have this, it's kind of a reservoir. We switch on the dipole trap. So it's filled from the reservoir. And because these are fermions, it means that each state, each vibrational state in this tweezer is filled by exactly one atom, assuming they are spin polarized, only in one spin state, okay? Because fermions cannot occupy more than one atom in a state, then this is what happens. And then the only thing I need to do is start to reduce the power of the tweezer. We get rid of the reservoir, and we eliminate all the high-lying states. If we are left with one bound state in a tweezer, then we will be left with one atom. If we're left with two atoms, etc. And this is how it looks in the experiment. So this axis is the final power of the tweezer. This is the value we actually go down with the tweezer. And this is the number of atoms we detect. And you can see these discrete steps which mark the discrete bound states which are left. So if we just stop here, we have one atom. If we stop here, we have two atoms, etc. So that's how you would prepare your tweezer with a well-defined number of atoms. I just want to mention that all the story I told you about the interaction and the flashback is also very interesting in the context of tweezers. That's a complicated and very interesting graph showing how many atoms are left for different magnetic fields in the microtrap. So this axis is the final power. So this is like this value. This axis is just this one. And so you see interesting stuff happening around the resonance. But one can also see that different types of resonances change differently. Yeah, please. So, okay, so I would say in a more realistic description, one would go from so one looks on the number of states in a three-dimensional. And then in a three-dimensional way, the axial part is the one dominating initially. And so one gets this degeneracy of the states, which takes you usually from 1 to 4. And above that, it's hard to see discrete levels. And one should also say that the fidelity we can actually prepare this is not very high. I would say maybe 65, 70%. We wanted it to be higher, but for some probably technical reasons, we cannot get to higher fidelities. Thank you. Okay, tunneling. So when you imagine maybe two truncated harmonic potential, like the blue one, this is maybe what you have in mind. And it's maybe close to what you imagine in quantum course of tunneling. But in fact, when we take two tweezers close by, they look more like the red one. They affect each other a little bit because of the wings. That's okay. We can still know pretty well what we expect from this, or at least theoretically, what we expect from this tunneling. To characterize it, what we usually do is we run simulation. These are simulation, okay? These are just time-dependent Schrödinger equations solving in 1D. And you can see, so let me walk you through. So what you see here, this is the potential. This is time. Here you can see one tweezer getting closer to the other one, okay? And then they stay for some time, and then they get far apart. And during this time, if I prepare, this is the wave function. This is psi square, so like density, if you wish. If I prepared my atoms in this tweezer, you see when I get closer to the other one, I start to initiate tunneling, and then I can take it apart and measure it. You can also say, you can also ask yourself, what happens if I start not from the ground state? Let's say I start from some excited state. This is an excited state, n equal 4 here, okay? And of course, you still see oscillation, but the frequency is different because the wave function is different. So it depends on the exact shape. So we've studied this theoretically, and these are examples of how different eigenstates behave as a function of the distance between the tweezers. More importantly, how would you see it in the experiment, right? So the sequence is more or less what you saw in the simulation. We start with one tweezer prepared with either one atom or more, depending on what do we want. Then we increase this tweezer depth to about 6 microkelvin. We turn on a second tweezer at some distance and wait. And then when we want to measure, we just take them apart and measure the population. Of course, we have to repeat this experiment many, many times. Each time we get one atom. It's not enough. Then we average over the signal. And these are average images showing different timings. And in the end, we get something that looks more or less like that. That's the duration. And here is the probability to find, for example, the atom in one of the tweezers. You can see clearly that one can get from that the frequency. I will not, because of time issues, I will not get into much detail on exactly the simulation on that, but let me just mention that it does not behave exactly like you would expect, or we. And to be even more frank on that, we don't fully understand. For example, we find that the oscillation, the tunneling oscillations are much stronger at distances where we would expect naively that they would die out already. So they persist to much larger distances. Well, larger, it's still like 2.5 micron instead of 2 micron, okay? But it's still significant. And we have several explanations. It might be related to the fact that these tweezers are, in the end, not exactly stable to the 10 nanometer scale that maybe they should have been, or maybe even less. But it also might be related to the three-dimensional nature of the tunneling. This is not a one-dimensional problem in real life. It's actually a three-dimensional process, and it might also be related to that. But yeah, please. Sorry?
Just give a simple explanation for the envelope.
Oh, yeah. Thank you. So there are interesting and less interesting aspects of this decay. Well, maybe interesting is not the word, intrinsic, okay? So let me give you first the first explanation. Why would the tunneling decay? So when you think about tunneling, I guess the simplest way to think about it is if you have like, let's say two wells, and you think about the ground state would be something like that, right? The symmetric one. The first excited state would be something like that. That's the asymmetric combination. Okay, so that would be maybe E0 and that would be E1. Now, if you want to think about an atom that started here, the best way to do it is just to add them. Right? Then this cancels and you start here. And then what you're actually saying when you talk about tunneling is just the fact that these two energies are different and then it oscillates, right? And that will persist forever. But when we do the experiments, there's no way one can actually prepare this state in an only two-state superposition. So now, in reality, you're actually going to add more states, more E3, E4, E5. And then these have different frequencies. And now when you merge different frequencies, it means you get dephasing because they have, right? So that's one reason why there is intrinsic decay of tunneling. You never, ever start the system with only two states. And then there are boring reasons. For example, fluctuations in the beam, things like that, which we try to win very carefully, but in the end. And I would just say not many groups try to look for in that, but any group that try to look for oscillation between tweezers, this is the scale of what they see. Like 10 oscillations is actually pretty large. Okay, so now I want to tell you about spatial adiabatic passage. To do that, let me start by reminding you, those who know it, and show you, those who don't, about stimulated Raman adiabatic passage, which is called stirrup. So stirrup is a very well-known concept coming from atomic physics, and it's also very much used in many experiments. So the idea is very simple. Let's say you have now an atom with three states, 1, 2, and 3. And let's say that the state 2 is radiatively decaying. For example, it's an excited state. That means that if you stay too much time at this state, you're going to decay and probably it's not going to do good things. And let's say you started in all your population being at 1 and you want to transfer it to 3. What do? So one way is let's put two fields, one omega 1, 2 and omega 2, 3, and just do 2 pi pulses. Transfer them to 2 and then from 2 to 3. But then my probability to lose the atom from 2 is fairly large. So there is another way to do it. And to see it, let's write the Hamiltonian. So here is the Hamiltonian with these fields. And if you diagonalize the Hamiltonian, you find that there is a state which is special. And we denote it by D because it's dark state. And it's special because it does not involve the state 2. It only involves 1 and 3. Because it only involves 1 and 3, we can write it in terms of the coefficients with the angle theta, which is given, the tangents of theta is given just by the ratio of these two fields. Initially, you start with all your atoms at 1. That means it's a sub state of this general state with cosine 1. To get to a cosine 1, I just need to make sure that omega 2, 3 is large and omega 1, 2 is small, or maybe 0. And that's it. That describes the initial state. But now, the idea is, if I change this theta gradually and slowly, I will stay in this state, because I'm now doing this adiabatically. And if I stay in this state, I will end up in the end with all the atoms being in state 3. But the point is, I never involve state 2. So that's good. Okay? Because I'm always stayed in a dark manifold. And indeed, this is the so-called counterintuitive pulse sequence. Here are the power, the intensity of the two beams. And if you follow that, it takes you from being in state 1 to being in state 3 with 0 population of state 2. And that is extensively used in many fields. How is it related to what I'm talking in this lecture? So, in fact, if you think about three tweezers coupled by tunneling, it's exactly the same system. One can map one to one. The tunneling is the coupling like omega 1,2 and omega 1,3. And I'm now looking only on one of the vibrational states here. So if you write the Hamiltonian of this system, it looks exactly the same like before, which means that if I now diagonalize it, I can identify again a dark state. But the beauty is that this dark state is indeed a state involving only state 1 and 3, and not state 2. So what does it mean in the sense of this transfer? It means that if I start with atoms in tweezer 1, I can move all of them to tweezer 3 without ever being in tweezer 2. That's a very confusing quantum effect. That in the end is really just because of the interference of the wave function on 2, which leaves the probability at 0. So we wanted to do this experiment. The way we do it is we control J12 and J23 by controlling the distance between the tweezers. So we start with one tweezer, which is filled. Then we open two tweezers, which are empty. These will be 2 and 3. And then to perform the counterintuitive sequence, we first take the empty tweezer 3 closer to empty tweezer 2. And only then we take the filled one and getting it closer. And this is how we actually implement the counterintuitive sequence by controlling the tunneling elements. To do that, one, of course, needs to do tunneling experiments and calibrate the tunneling frequency to know exactly how to do that. More importantly, what I want to maybe stress is that the fact that we have at least 10 oscillations before it actually decays is important for your ability to actually perform an adiabatic passage. To be adiabatic, you need to be longer than the oscillation time. And 10 is about the time you really want to be. So that's good because it means we can be in this regime. And let me show you the results of this. So this is, again, the same experiment I alluded before. At each and any given time, we can take the three tweezers and measure their population. After averaging, this is what you see. So we start with all the atoms at tweezer 1. And you see that as your process progresses, the atoms move from tweezer 1 to tweezer 3 with minimal occupation in the second tweezer. Now, in order to convince you that this is really an adiabatic process, I switch the order of the two pulses. So instead of doing it in the counterintuitive, I now do it in the intuitive sequence, which in fact just means we pass the atoms to the second tweezer and then to the third one. And as you expect, it's becoming kind of a mess. Perhaps one can fine-tune the parameters to achieve high fidelity also in here. But the main point is that it requires fine-tuning of the two pulses. While here it's really a robust process, which you can see by tuning the parameter space and see a large range of parameter space where indeed you get high fidelity. So indeed it's an adiabatic process which does not require fine-tuning. Okay. I want to give you another, yeah, please.
Tweezers closer and farther apart rather than just like tuning powers to change the time.
Okay, so it's not matter of both are easy the same way. I mean, we can control the position and the height independently, so this is not a problem. But if you really want to implement and by the way, the changing we do it sometimes, and it's interesting by its own sake. But to implement these type of model, one really wants to keep them degenerate. We actually do specific calibration process to make sure they are exactly degenerate. For each two, we take the oscillation, make sure it equilibrate to 50-50, and etc. One could think about playing with another model. I mean, this model is, of course, infinitely rich. But it's completely different process. If you would do, by the way, this process, you would still do adiabatic following, but you would probably go from being with all the atoms in one to the other, because this is the adiabatic process in this case. But I'll come back to your question in a second, because I think one can use it to do, for example, beam splitting. So in the atomic interferometry, I'll be back. Yeah, please.
I haven't seen this specific technique before. This sort of stir up like, but with different traps. Is that originally from your group? Did you guys put it in?
So the suggestion came. Let's see. I think it's here probably. So the suggestion came. You can see here the papers. They came already at 2004. This is a very good review in 2016, if you want to see like the history of the idea. So definitely the idea to map this and do this did not come from our group. We were the first to implement it, and I think it had to do with the new technique that was developed to control tunneling in a very precise manner. That was essential here. Okay? You're good? Okay. I just want to very briefly mention that this spatially adiabatic passage looks like it's so the idea that it's a stirrup is of course is understood, but I want to make another comment about it, and it's actually its connection to topological pumping. It's going to be a brief comment, although one can discuss this to a very large extent. But the idea is the following. There's a topological model of a chain in 1D called the SSH model, the Su-Schreifer-Heeger model, which originally was devised to describe the polyacetylene molecule. And it's a very simple model that has like two tunneling elements, J1 and J2, in a linear chain. Okay, so it's like a variation of the Hubbard, the one-dimensional Fermi-Hubbard model. People know that if you take an even number of sites, this chain has a non-trivial topological phase, depending on the value of J1 and J2, or the ratio between them. What people know less is that if you take an odd number of sites, these models always have an edge state. But it depends on whether it's on the right or left side, depending on whether J1 and J2 are actually larger, or whether J1 and J2 is larger or smaller. So what we are saying is that spatial adiabatic passages can be considered as edge-to-edge transfer of this edge mode in this odd side SSH model. And in fact, what happens is that you change J1 and J2 adiabatically, and you move the edge states from one side to the other. And in that respect, it can be generalized. One can think of doing this in 5, 7, 9, etc. It will still work the same in the sense that atom will be transferred from one side to the others completely in fidelity approaching 1 in the adiabatic limit. Of course, the adiabatic limit will become progressively hard to be in. And moreover, if you now add another parameter, which will be the energy detuning, then you can make this model even richer. This is called the Rice-Melle model, again in 1D. And the Rice-Melle model is the model which is being discussed when people talk about towless pumping, for example. And the idea is that all these models will support edge-to-edge transfer of these edge states. And so in that respect, what we have done here is really just the first step, and one can extend it to topological models. And this is one of the things we are working on now. So it's a very interesting direction. And yeah, in the sake of time, I think I'll skip the rest of the details. If you want, we can get back to it. I want to talk now about how it's related to atomic interferometry. And I mean, what I showed you is essentially an adiabatic following. And now I want to show you how this is done, how it can be used to do beam splitting and atomic interferometry. So in one slide, atomic interferometers are already very successful. The way they usually work is by throwing up a bunch of atoms and letting them doing ballistic motion, and then splitting them in momentum space using Raman beams. So many limitations exist, of course, including the fact that the path is only geodesic. If you want to probe them for a long time, you need to toss them up very high, so you need very large systems. And of course, they tend to spread out, so the resolution is very poor. Having said that, you should probably be aware that many important results came from this type of interferometers, including measurements of the gravitational constant, fine structure constant, the Aharonov-Bohm effect. And my favorite in particular is this testing of the equivalence principle. But all of these are done with this type of interferometer. What we would like to develop is a new kind of interferometer where the splitting is done in real space and the atoms are kept all the time trapped in tweezers. So you can imagine the atom starts in a tweezer, split. Each atom is being in a superposition in two tweezers and then recombine and the measurement is done. So the splitting and recombining is really a key aspect of this interferometer and how it is done. And this is related to the adiabatic following I was just showing you. So here's a simple way, and I get back to your question. If you start with two tweezers, let's say, and only one of them has the atom inside. So here is an example where the atom is here. Let's say it's the lowest energy, okay? And now what we're doing is we're actually taking the tweezers closer. So the tunneling now couples them, and we also bring them to be degenerate. Now the ground state is the symmetric one. If we do adiabatic following, it means we started from the ground state, we follow the ground state, and it means we are actually splitting the atom in a superposition. And it's robust because it's adiabatic. So that's an idea of how to do the splitting. The recombining is just a time reversal of this. So here is an example of how we measure. This is the interferometric loop. You can see the atoms get into the splitter, split into two. If now you introduce a phase in the center, for example, here it's pi over 2, then if you time reverse the splitter, you get the atoms output in the two, equally in the two outputs. So just measuring the population in these two arms give you the interferometric measurement, which is very sensitive to the phase in the middle. And it works for the excited states as well, because each behave like a different manifold. We have another idea of how to use three tweezers, and you can say, why make it more complicated? So this idea of using three tweezers actually has the interesting ability to detect errors. So you end up with the atoms split in the two external tweezers, and then if you measure the internal tweezer, you can actually know if you have an error. If you find an atom there, you know that something went wrong. So it's a beam splitter with an error detection. And yeah, we have some preliminary results on this in this particular setup, but maybe again, in sake of time, we'll continue. What can you do with this particular type of interferometer? Well, we imagine doing very precise measurements that require very good position accuracy. For example, if you take a test mass, like half a sphere of tungsten, you can easily measure the gravitational force by looking on the differential phase imparted on the two arms, which are separated by about even 10 millimeters would work, but depending on what's the, if you take it to 50 millimeters, you can get very good accuracy in determining the gravitational force. Another example of what you can do with that, you can take one arm close to a surface and the other one, let's say 100 micrometer away. And then you can be very sensitive to forces between the atom and the surface, namely the Casimir-Polder forces. This type of forces has never been measured accurately in a model-independent way. And this can be a very straightforward way to measure the forces acting between the surface and the atom. And lastly, I want to close by showing you how can you use this interferometer to measure quantum gravity effects. So this will be the final thing. So by now, I just introduced the idea that you can take a mass and split it. The atom that I discussed, I did not discuss any internal states. It's almost as if it was just a point mass. However, now we can introduce back the internal degree of freedom that we have in the atom. And specifically, we are talking about how atoms are used as atomic clocks. So I hope most of you already know that atoms are used as atomic clocks. This type of clock actually uses the lower hyperfine level of cesium, which is now the standard of how you measure time. And this is the most accurate clock. But more recently, people have been using these optical clocks where actually they measure the transition between two states which are optically different than each other. So these transitions, which has very large frequency separation, give you hence very much higher detection accuracy. But the key point is that the atom needs to be trapped in a potential that does not affect this transition. This is called the magic wavelength. It's the wavelength at which the polarizability of these two transitions is exactly the same, and so it does not depend on the trapping, the transition frequency. And so people have been built optical atomic clocks that now reach the sub 10 to the minus 18 relative accuracy. It's really mind-boggling. We want to use this idea, the possibility to use these optically separated states to do the interferometry. And the idea is the following. So here is again the interferometer I showed you before, but now I also introduce the internal state. Okay, so the color stands for the arm. Which arm are you? Okay, blue is the upper one, red is the lower one. But you also have the internal state, which is depicted as this blocks here. So the interferometer goes the following. You start with the atoms pointing up in the ground state, okay? Then immediately before you split them spatially, you give a pi over 2 pulse. So you do a Ramsey on the internal state. So now they are here. Then you do a pi over 2 pulse on the external degree of freedom. So you have both Ramsey on the external and internal degrees of freedom. Each atom is splitted. Each clock is splitted coherently. Let's say this is gravity. So this is higher than here. It means that they are not in it's not a uniform metric. The clock ticks differently because of the gravitational redshift, right? Clocks that are in a different height tick differently. This means that this clock ticks differently than these clocks. And in the end, you recombine them, and also you can read the two observables, both what is the output port, and the other one is what is their internal state. And it turns out that if you do correctly the math, you can see that these two observables, namely what is the probability to get out in one of the ports and what is the probability to be in the ground state, give you all the information about whether you are coherent. So this detects the coherence between the beams, while this detects the redshift. You see here, this is the redshift which arises due to the difference in gravitational potential. So the end result is that you can measure both whether the splitting is coherent and whether the clocks ticked in a different rate. And so we did the math with the ytterbium 171 is one of the atoms that are being used as atomic clock together with strontium. And we think it's a great atom to actually be used in this type of interferometer because it's heavy. You want the atom to have a large mass. And it has this metastable state that can be used as a clock. And the key point here is that the tweezers needs to be in the magic wavelength. So they should be trapping the atoms, but do not affect the difference between the clocks. And this way you can actually very sensitively measure whether you have coherent splitting, even if you don't have a complete control over the phase. Even if the phase is completely random during the interferometer, you can still know whether you have a coherent probability or incoherent. So you can measure both the gravitational redshift and the coherence of this interferometer. If you want, I know this was very brief, and if you want to know more, you're welcome to look in this publication. And so I'll finish by saying that we are actually just started building a new tweezer machine with the Terbium 171, which is also a fermion. So it's kind of interesting for many reasons. It's also an interesting qubit. And I'll just give you the summary. I showed you how adiabatic passage can be used to do transfer. It can be useful for quantum technology. It's also interesting from fundamental point of view for its connection to topology. I show you how it can be used to do beam splitting and recombining, and how this can be used to do atomic interferometry. And lastly, I showed you how this can be combined with internal degrees of freedom to also actually measure the atomic clock. And this is actually exciting, this direction, really, because I think it's the first time that one could actually do a measurement that is sensitive, that creates a quantum superposition in a non-uniform metric. So it's really the first kind of quantum gravity experiment one would do. And there are theories out there that, for example, predict the collapse of the wave function because of non-uniform metric, and this could be probed in this type of experiment. And yeah, let me just finish by showing you the people who actually did the work. So Yanai, this was his PhD work, building this whole system of potassium-40 tweezer machine. He's now graduated. Elad, which was a master's student and continued PhD on this. And today, the current generation is Guy and Dor. And with that, thank you for your attention.